In this video, we'll be looking at the simple harmonic motion. So this is a topic that we'll be looking at. So the first thing that you need to understand, we need to know the definition of simple harmonic motion. So we will define what a simple harmonic motion. So we define in this way: a simple harmonic motion is a type of periodic motion where an object moves back and forth. So the object moves back and forth, right? Around a central or center equilibrium position. Right? So you say is a type of motion, is a type of periodic motion where an object moves back and forth around the central position. So that is what we call the simple harmonic motion. So in another way, I can say that the acceleration is direct proportion to the displacement. That's what we call the simple harmonic motion. Then this simple harmonic motion, it goes in hand with what we call Hooke's law. So what does the Hooke's law states? Hooke's law states that the force applied on an object is equal to the displacement of an object, right? So the force that I will apply on an object, it will be equal to the compression or the displacement. The object will be displaced or compressed. That's what we call Hooke's law. And these are the main things that you need to take note of when it comes to what we call Hooke's law. So now we need to go into detail about what they meant, right? So since we are about to go into details about what they meant, remember what we'll be dealing with here is that we'll be dealing with mainly with a spring, because that's where the Hooke's law applies mainly about the spring or any elastic objects, right? Okay, now let's go to the another thing. I said that Hooke's law states that the force is equal to negative kx. So this is the displacement, and this, it is what we call the force. And this force, we call this force as what we call restoring force. And this is what we call the displacement. And this is what we call the spring constant, like that. So you have the restoring force, the spring constant, which is here, and also the displacement, which is that one. So now we really need to know if when is this restoring force positive, and when is this restoring force what? Negative. So that's where we really need to know. The question is, when is the restoring force positive and when is the restoring force negative? So in here you have a spring which is here. So this is the spring that you're having, and I am forcing this spring to go in this direction. So when I'm forcing this spring going in this direction, it is telling me that the restoring force, so if the applied force is going in this direction, meaning that the restoring force is going in which direction? In the opposite what? Direction. So in this situation, this side is the negative side. So meaning that when you are pushing your object, or when you're applying the force in the positive direction, meaning that your restoring force will be negative, like that. How about when you apply the force going in this direction? So when you're going in the other direction, meaning that the restoring force will be positive, because it is be going in another what? Direction, like that. So these are the main differences that you need to take note of when you're dealing with what we call the restoring what? Force. So and we can able to calculate what we call the acceleration when it comes to that. So we can able to do what we call the acceleration. Remember, the restoring force, it is what? Negative kx. Now we need also to know how to calculate this, how to calculate the acceleration of an object at which an object is what? Moving. Remember, force is equal again to mass times the acceleration. So where there's force here, I'll replace with that, then this, then I will divide by mass. Meaning that acceleration, it is negative kx over m. So that is how you calculate the acceleration. And the other thing that you need to take note of when it comes to that, it is what we call the spring constant. Now the question is, how do we calculate this spring constant? And the spring constant, it has the units, which is newtons over meter. That is the units of the spring constant. So we can able to calculate the spring constant if this is how we calculate the spring what? Constant. So if you look, you have these two springs here. These two springs here, and these two springs here are they're in what? They're in parallel. So you have two springs that are in parallel. In this situation, for me to calculate the total spring constant here, I'm going to say the spring constant for this one. I'm going to say again the spring constant for this one. So for me to calculate the total here, I'm going to say K1 plus K2. So this is the formula that you use when you are calculating what we call the spring what? Constant, which is in what? Parallel. So when it is in parallel, this is the spring constant that we use. But if the springs are in series, meaning that the springs now are in series, so this is the first one, this is the second one. So we have this spring and this spring. So the question is, how do I calculate when I have something that is like this? So in here, this is where you say 1 over k, which is the total is equal to 1 over k1 plus 1 over k2, like that. So that is what we call the total, or calculating the spring what? Constant. So that's what you do when you have something that is like that. Okay, now let's look at some other important things that we really need to take note of. I'll call these ones as the properties of what? Simple harmonic what? Motion. So the properties of the simple harmonic motion, take note of, they have what we call period. They have also what we call the what? Frequency. They have also what we call angular frequency, like that. So how do we calculate the period? We calculate the period by saying t is equal to 1 over t is equal to 2 pi over angular frequency, or t is equal to 1 over frequency. In another way, this one again we say frequency, it is angular frequency over 2 pi, like that. Or in another way I can say frequency is equal to 1 over period. Then when it comes to the angular frequency, we calculate this one by using this, which is mass over, supposed to be spring constant there, over mass, like that. So that is the formula that we use. Then the same period, we can also calculate the period by saying 2 pi is equal to mass over k. Then the frequency, again, we can also calculate by saying 1 over 2 pi, then square root of k over mass. So that is also the another formulas that we use when we are calculating what we call the what? The frequency, the period, and also the angular frequency. So those are the main things that you need what? To take note of. So I can say the other part, it is what we call the simple harmonic motion graphic representation. So simple harmonic motion graphic what? Representation. So in here I can say that simple harmonic motion graphical right representation. So when it comes to this simple harmonic motion, they are represented in this equation, or they are summarized in this equation, right? So the equation that they are summarized in this equation, which is amplitude cos. Then this side it is angular frequency times time, then the phase shift. So here, this is what we call the amplitude, and this is what we call the angular frequency, and this is what we call the what? The time, and this is what we call the phase what? Shift. So we have the amplitude, angular frequency, time, and also the phase shift, like that. And this formula that I have given out, this formula, it is what we call it as for the displacement. Okay, so this is just a simple representation of the simple what? Harmonic motion. Now this representation, it can be also represented in the form of The first one, I can say the displacement. That's the first one. The second one, it can also be represented in the form of what we call the what? Velocity. And the third one, it can also be represented in the form of what we call what? Acceleration. So the displacement, this is the one that we use. When we talk about the velocity, this is the one that we use. So say negative, when you differentiate that, you're gonna have to have Wt, then sine. This is the formula that we use. When it comes to the acceleration, negative W squared, then cos. Like that. So these are the formulas that we use, and this is just for the displacement, and this is just for the velocity, and this is just for the what? Acceleration. Now you need to also to take note of, we have what we call maximum what? Displacement. Let's start with the maximum displacement. Maximum displacement. So we have maximum displacement, which is x is equal to what? Amplitude. Again, we have also what we call maximum velocity. So the maximum velocity, it is v is equal to amplitude times angular frequency, or sometimes it can be amplitude then the square root of what? K over mass. Then the other one, it is the maximum acceleration. So this is the maximum acceleration. So the maximum acceleration in this situation, it is a is equal to what? A then squared. In another way, I can say this is a k over mass, just like that. So those are the two differences that you need to take note of. You need to take note of on those ones, right? So those are the main things that you really need to take note of. Okay, now the other part that you need to take note of, just know that simple harmonic motion, again, because these ones, they act like waves, right? Or in short, they are waves, but the waves that are under what? Moving in the what? X-axis. So since they are the waves that are moving in the x-axis, meaning that they have what we call energy. The question is, what kind of the energy do they have? They have what we call potential energy and the kinetic what? Energy. Now the potential energy here, it is 1 over 2, then kx squared. Then kinetic energy, it remains to be this. Now, how do we calculate this velocity? We calculate this velocity by using this formula, which is here, which is k over mass, then displacement, that is amplitude here, squared minus what? X, like that. Or you can say angular frequency, then this part here, just like that. Again, we have also what we call total energy. So total energy is the potential energy plus kinetic energy. So meaning that you are going to add potential energy plus kinetic energy, but they already made the formula, the simplified formula for you, which is this formula. So the total energy in that situation, it is what? Is equal to 1 over 2, then Ka squared, just like that, straight and forward, just like that. So that is how you calculate something that is under that. Okay, Now let's go to the other part, which is the most important part. Now, the only thing that I want you guys to take note of is just this part. When we have what we call simple pendulum and the other one is what we call physical pendulum. So in here, when you have this, what you need to take note of is that angular frequency of the simple pendulum, it is gravity over length. Then the angular frequency of this one, it is mgd over moment of inertia. So this means that the period when it comes to this side, it is 2 pi then square root of L over G. Then period, the frequency, it is 1 over 2 pi then G over what? L. Then this side, it is period is 2 pi then square root of what? Moment of inertia over mdg. This d is a distance or the middle distance, g gravity, m mass, then I moment of inertia. Then the frequency, it is 1 over 2 pi, then what? Moment of mdg, like that, then moment of inertia, just like that. So these are the main things that you need what? To take note of when you are dealing with this. That's all. So for more, make sure you subscribe to the channel and also like the channel.